Okay, this is the last checkpoint in SHM. Start off with some basic definitions. So forced vibration is one which is caused by a periodic force. That's a force which is itself changing its strength. Resonance is a large amplitude vibration caused when the driving frequency, okay, these are the crucial terms really, the driving frequency is equal to the natural frequency. Okay, damping is a force which opposes the motion. So the most obvious example of damping is air resistance. Air resistance is always going to be going in a direction which opposes the way the oscillation is already moving. And the effect of damping on resonance is that it reduces the amplitude. Okay, also in the mark scheme here it accepts that it reduces the sharpness. Okay. This is the crucial graph where we have the driving frequency, we have the amplitude of the driven vibration up the side, starts low, goes up to a peak, comes down to a very low value, okay? And this peak here is the crucial bit because this is the natural frequency here. When the natural frequency and the driving frequency are equal, this is where we get resonance. If I just change the pen colour, okay, that's a lightly damped vibration. Here's a heavily damped vibration. It follows the same sort of shape. Okay, but what we get is a much lower peak at resonance. This is not a particularly difficult question, but a lot of people get confused with it. Okay, so we've got a car and suspension, which is a mass spring system. We've got 4 people with a total weight of 3,000 newtons get in the car, which itself already weighs 6,000 newtons. This squashes the springs by an extra 50 millimeters. Okay, so our first step is to work out the spring constant. So we'll remember the equation, F equals K delta L, but the crucial thing is, well, what force do I want? Well, this force here, 3,000 newtons, has stretched them by an extra 50 millimeters. So what we need to do is K equals F over delta L, but this F is the extra 3,000 newton force, which just stretched it by 50 millimeters, 50 times 10 to the minus 3 meters. And that gives us a spring constant of 6 times 10 to the 4 newtons per meter. But then in the next situation, okay, this is a mass spring system. We're trying to find the period of oscillations, and they've helpfully told us the answer. So we know we've got a t equals 2 pi root m over k kind of calculation. But again, in my experience, it's this mass which causes all the trouble. So if we do W equals mg, then we know that mass is weight divided by gravity. But which weight do we want? Well, it's the whole thing that's oscillating. The mass is the weight of the mass of the people and the mass of the car all add together. So we've got to do 9,000 divided by 9.8. So this gives us t equals 2 pi times the square root of 9,000 over 9.8 times 6 times 10 to the 4. Okay, stick all that in your calculator. Then you do find the period, comes out at 0.8 seconds. Okay, so this car then drives down a road at 20 meters per second with 16 meter apart hump. If you get this one wrong, to be honest, it's just embarrassing. This is speed equals distance over time, so time equals distance over speed. The distance is 16 meters. The the speed is 20 meters per second. That gives you 0.8 seconds between the humps. Okay, if you do this the wrong way around and get 1.25, you want shooting because the humps are 16 meters apart. The car's travelling at more than 16 meters a second. Your answer has got to be less than 1 second between the humps. Okay, also the whole point, and we worked out before, the natural frequency or the natural period was 0.78. So those two numbers are very close together. Okay, so the point of this is that the natural frequency is approximately equal to the driving frequency. So you will get large amplitude oscillations. Okay, question 3. Again, nice easy one hopefully if you're in the middle of a topic on this. So this is a Millennium Footbridge. You've probably seen a video of this. The effect that they had when they built this footbridge was resonance, because the people walking across it swayed forwards and backwards with a frequency that was very close to the natural frequency of the bridge. So why will this become particularly hazardous? Okay, again, same answer really as before. When the driving frequency is equal to the natural frequency, you'll get large amplitude oscillations and might cause damage to the bridge, okay? So, or of course people might fall off the edge. Okay, there are 2 marks here for talking about the natural frequency and the driving frequency. That's what there's 4 marks for this question. Things that you might do to change this, well, change the natural frequency. You can put methods for doing that, for example stiffening the springs which support it at the end, or you could do what they did initially, which is just to reduce the number of people that were allowed to cross the bridge. Okay, last question is a classic resonance kind of experiment. So you've got something with a natural frequency of 1.5 Hertz. You connect it to some kind of vibration generator up here which makes it oscillate. And the key thing here is with reference to amplitude, frequency and phase. Okay, talk about each of those 3 things. Now you'll notice they give you a few chances here because there's only 6 marks. So if you get 2 out of those 3 for each, you'll be okay. But your perfect answer really should include some information on each one of these 3 things. So you've got 9 possible marks to go at. So in terms of the amplitude on the first one, we look at our frequency. It's much lower than natural frequency. So the amplitude will be small. Okay, but not just small. It will be approximately equal to the driving amplitude. Okay, because as this goes up and down very slowly, okay, this will just go up and down the same with it. The frequency will be approximately 0.2 Hertz because it will just vibrate with it, and the phase will be in phase. Okay, here's our second one that you'll have done most. This is resonance. So at resonance, the amplitude will be the amplitude will be large. Okay, the frequency will be 1.5 Hertz because the natural frequency and the driving frequency are the same. And the phase, you'll have talked about this hopefully, it'll be 90 degrees out of phase. When you vibrate the top at 10 Hertz, the amplitude will be small again. Okay, smaller than this because it won't be vibrating up and down the same amount this vibrates, so this will be a very small amplitude oscillation. The frequency is a bit tricky on this one really. So probably some sort of vibration at about 10 Hertz, but a bit of a mess. And the phase, they will accept just out of phase. They suggest possibly by pi, so it's in antiphase. Okay, the next part of this question should be really easy. Hopefully this is the time to travel between the 2 humps for a car. It's going at 20 meters per second and the humps are spaced 16 meters apart. So this is speed equals distance over time. Time equals distance over speed. 16 meters apart, 20 meters per second. Gives us a time of 0.8 seconds between the humps. Okay, I've seen lots of people get 1.25 seconds, okay. But to be honest with you, you should be embarrassed to do that because the 16 metres between the humps, the car's travelling at more than 16 metres per second. Should be fairly obvious that the time is less than 1 second. Also, you might want to think what the whole point of this is. Well, this is a question about resonance, and you notice we've got a period here of 0.8 seconds.